Introduction. Heat exchangers are devices that facilitate the heat transfer and energy flow from a hotter fluid to a cooler fluid. The heat transfer that occurs within a conventional heat exchanger is difficult to observe and often appreciate without the use of computer-aided engineering, such as computational fluid dynamic packages and software. The purpose of the upcoming investigation is to perform a comparison using thermal analysis between a conventional shell heat exchanger and a tube heat exchanger using both the countercurrent and co-current flow configurations. By doing this, we will be able to detail the relevant modes of heat transfer that occur, and in addition, it will be determined which heat exchanger configuration will be able to operate the most successfully within the confines of a real-world application. It is currently hypothesized that a heat exchanger has the potential to be used in a power plant to extract heat from a waste source which is currently identified as flue gas. It will be determined if flue gas can potentially be used to preheat the water, which will create the steam for the plant to be used for chemical reactions as a catalyst. If successful, it would result in potential savings for the plant due to less energy being required to boil the water. The interest, however, in this research arises when the efficacy of a heat exchanger comes under scrutiny. To be able to perform an idea of a successful thermal analysis proves quite invaluable and inherently aids in the further development of science and technology. Scientific advancement can prevent pernicious environmental activity, as a heat exchanger optimizes energy consumption by redirecting heat away from areas where it is not needed to areas where it is needed. Many benefits may arise from the research that will be undertaken, such as uncovering a possible path to greener engineering practice where the general scientific community concur with the notion of becoming more environmentally friendly. The objectives of the simulation are mainly twofold. 1. To determine the rate of heat transfer that occurs within selected heat exchanger configurations, and 2. To determine what effect using flue gas has on the performance of the heat exchanger. The results are expected to be quite promising and will prove the fact that the countercurrent flow is the most efficient and effective flow choice when compared to other possibilities such as co-current, cross-flow, and hybrid flow. Heat exchangers are devices that make use of basic thermodynamic principles and conventions to facilitate the effective heat transfer between two or more fluids. The zeroth, first, and second laws of thermodynamics are all present and comprise the theory behind the underlying physics of how a general heat exchanger operates. These basic principles are present in all heat exchanger classifications, regardless of the design type or application, and heat exchangers employ all of the three modes of heat transfer, namely conduction, convection, and radiation. These energy-optimizing devices can broadly be classified based on their design characteristics, which are summarized in the flowchart found on this slide. One can see that flow configuration, construction method, heat transfer mechanism, and type are the four design characteristics that are used in order to classify the different types of heat exchangers. For the purpose of this investigation, the flow configurations chosen was concurrent flow and countercurrent flow, and the type of heat exchanger simulated was the shell and tube heat exchangers. The applications of heat exchangers are so vast that these devices are able to be found in many engineering sectors and industry. Heat exchangers feature in vital sectors of the industry such as in HVAC application, energy optimization, and in temperature regulation and control. These devices also perform functions in steam generation, industrial cooling processes, cryogenic and furnacing applications. They can be found in power plants, chemical processing plants, in petroleum refineries, and they can be found in aerospace and automotive industries.
The shell and tube setup was chosen for its simplicity and its ability to simulate both countercurrent and co-current flow. The geometry that was used was created on ANSYS Design Modeler. It was required of us to create the flow domains for each specific fluid. These fluidic volumes were also generated on ANSYS Design Modeler. The dimensions for the shell and tube were taken from an example seen on YouTube for an application within a power plant. These can be found in the accompanying report. A mesh of 0.27 square meters was used as this was sufficient for mesh-independent simulation runs. Numerous iterations were done due to the computer-aided drawing showing errors and inconsistencies upon simulation. After revising these results as a group, a consensus was reached that the results were erroneous. It was later found out that the model contained gaps that output somewhat strange results. Inspection of the model led to a smoother and more consistent model which simulated the scenario to an acceptable degree of accuracy. The material selected for the shell is aluminum and the material selected for the inner tube is copper. Aluminum was selected based on what was seen from tutorials on heat exchangers earlier in the course. However, we recommend the use of steel for the shell geometry because of its lower thermal conductivity. This decision would result in less heat transferred to it, thereby minimizing heat loss from the fluidic system for the purpose of the previously mentioned application. Steel is also cheaper to use for the shell material since this part of the exchanger has the most surface area. Copper is an ideal material to controllably conduct heat from the hot fluid to the cold fluid due to its high thermal conductivity. In retrospect, we have learned that a good simulation hinges upon a well-generated computer-aided model, as well as a good understanding of heat transfer by conduction and convection between materials of different thermal and flow properties.
We simulated the steady-state solutions and transient solutions for both the co-current and counter-current configurations to try and determine the optimum heat exchanger configuration. The simulations were done on ANSYS Fluent with the following settings. Energy was put on, gravity was set to negative 9.81, the realizable K epsilon viscous model was used, and all residuals were set to 1 times 10 to the negative 5 to have good convergence results. These settings were common for both the steady-state and transient solutions. The fluids that were selected were carbon dioxide and water. The reason for the selection was based on power plant applications where flue gas is used to preheat boiler feed water. The ANSYS software does not have flue gas in its database and hence has selected carbon dioxide, which is the main gas that is found in flue gas. The carbon dioxide flows on the shell side at an inlet velocity of 1 meter per second and a temperature of 200 degrees Celsius. The water flows on the tube side at a flow rate of 0.4 meter per second and a temperature of 21 degrees Celsius. The temperatures are selected based on what I have personally seen during my vacation work at a platinum refinery plant, and the flow rate was selected based on the basis of matching the capacity rates for the fluids. The capacity rate being calculated as the flow rate multiplied by the specific heat. In the result, the temperature ranges for the animations had to be set to different values for the tube side and shell side animations so that the change in temperature for each fluid could be more distinct. The steady-state solution had 100 iterations, which resulted in the residuals being close to the required value of 1 times 10 to the negative 5. The transient solution had 25 iterations for each frame. This was enough to achieve the actual residuals of 1 times 10 to the negative 3. This was accepted as it's an adequate value, and the computation time that's associated with it was not too long.
This slide demonstrates the comparisons in results from the simulations of co-current flow on the left and counter-current flow on the right. Here is a simulation of the counter-current heat exchanger, with cold water flowing through the tube in the middle and hot carbon dioxide gas flowing through the shell at the top. While using the exact same conditions as for the counter-current animation, this simulation shows the co-current flow.
For simplification, the temperatures will be converted from kelvins to degrees Celsius. For the co-current heat exchanger, the inlet hot temperature is 200 degrees Celsius and the outlet hot temperature is 110 degrees Celsius. The inlet cold temperature is 19.95 degrees Celsius and the outlet cold temperature is 104.8 degrees Celsius. The temperature of the cold fluid changes dramatically halfway throughout the length of the heat exchanger. From this point, it approaches a steady state temperature of 104.85 degrees Celsius. For the counter-current heat exchanger, the inlet hot temperature is 200 degrees Celsius and the outlet hot temperature is 91.45 degrees Celsius. The inlet cold temperature is 19.95 degrees Celsius and the outlet cold temperature is 104.85 degrees Celsius. It is observed that there was a greater exchange of heat due to the outlet temperatures of the counter-current heat exchanger being lower than the co-current heat exchanger. For the calculations, we'll be using the same values as the simulation. Using the equation for the log mean temperature as seen in the slide, we get the log mean temperature for co-current heat exchanger to be 51.39 degrees Celsius and the log mean temperature for the counter-current heat exchanger to be 82.76 degrees Celsius. As the log mean temperature for the countercurrent heat exchanger was greater than the log mean temperature for the co-current heat exchanger, this means that there's a greater difference between hot and cold temperatures throughout the length of the heat exchanger in the countercurrent case. As temperature difference is the driving force of heat exchange, there will be more heat being exchanged in the countercurrent case. Thus, these results reinforce the countercurrent heat exchangers are more efficient than co-current heat exchangers.
An interesting result from these heat exchangers is it can be seen that countercurrent heat exchangers can be used for both heating and cooling applications. This is important as the heat exchanger may be used to remove heat from a certain working fluid and make it cooler, as may be designed for an air conditioning unit, or may be used to add heat to a working fluid and thus be used as a heating system. An interesting observation that can be made concerning the temperature difference is that the range for the tube is significantly larger than the range for the shell. This is due to the difference in volumes and surface areas. Over a specific length, the tube has a smaller volume of fluid flowing through it and thus is more susceptible to temperature changes. The fluids were also seen to play a part. While carbon dioxide was seen to have a smaller temperature gradient, the water had a much larger temperature gradient. This comes down to the thermal capacities, thermal conductivities, and other fluid properties of the fluids used in this simulation. The aim of this report was to simulate heat transfer in a heat exchanger using a computer simulator, namely ANSYS. For the simulation, two heat exchanger configurations were investigated, namely the countercurrent and co-current configurations. The fluids that were used were water and carbon dioxide. It was determined that countercurrent configuration was more effective at heat transfer, a result which is in line with the principle of a greater log mean temperature, which is the driving force for heat transfer. Overall, the simulation was successful at demonstrating the heat transfer in a heat exchanger that is predicted. These are the members of our team and what they contributed to this project. Thank you for watching and we hope you enjoyed.